Mankind has always cooked food using everything from campfires and barbecues to gas and electric stovetops. Now he can use an induction cooktop. It doesn't need a fire, a flame, or a red-hot burner. It uses innovative cooking technology our ancestors never dreamt possible and would swear was pure magic. An induction cooktop doesn't use traditional cooking elements above or below the cooking surface. It uses copper induction coils that generate high-frequency electromagnetic fields. These fields excite the molecules in the pan, creating heat only in the cookware itself. That's why the yolk remains cold, and only what touches the pan cooks. The magic starts with a punching press that stamps computer-generated shapes into sheets of cold-rolled steel. These cutouts fix the position of the induction coils that sit under the glass surface. A press brake bends the four sides of the steel so it will hold a glass ceramic top in place. In the meantime, a machine spray paints the burner box, the visible part of the cooktop. A technician affixes the labels and the power cord onto a housing box that will conceal the induction electronics and coils. She secures the power cord for strain relief. She then attaches the power cord ground and the system ground wire to the housing box. She places a cover on the box and screws it into place. Another technician puts together the induction electronics. These assemblies of circuit boards, cooling fans, and semiconductors drive the cooktop. She covers the electronics with insulation and a metal carrier plate that will support the induction coils. Then she feeds the user interface wires through the top of the coil carrier plate. The technician screws the carrier plate and the electronic assemblies together, then grounds the electronics. Protective tape around the openings will prevent the user interface wires from rubbing against the coil carrier plate. And some insulation will protect the electronic assemblies. She closes that side of the electronic housing box and attaches all the power cables. A sheet of insulation goes on the flip side of the box, where she mounts the electromagnetic coil assemblies. The iron slugs on the back of each coil pod help distribute the electromagnetic energy to the cookware evenly. She connects the coil assembly to the system board. Then she places the remaining 4 coil assemblies onto the carrier plate and connects their leads to the system board. Meanwhile, another technician assembles the components of a glass touch user interface panel. She connects the interface to the steel holder that was bent into shape at the start and is now attached to the black burner box. She covers the cooking surface and control panel with an attractive stainless steel frame, then connects the system board to the control panel. She closes up the other side of the burner box. Then she bolts everything down to complete the cooktop. A technician tests the unit. Using a metal object to activate the electromagnetic field, he verifies that the controls respond properly. He makes sure all 5 induction coils are working and the power output from each coil is correct. The control panel confirms it's a success. Clean, safe, and energy efficient, induction cooktops make cooking food quick and easy. Jawbreakers, also known as gobstoppers, have preoccupied candy lovers for decades. You pop one in and slowly suck or chew through up to 10 layers of colors and flavors. Sometimes there's bubblegum in the middle for an even longer lasting finish. The larger ones are just for show. Most Jawbreakers are about the size of a golf ball. To make their bubblegum centers, a worker blends synthetic rubber with powdered resin, which will dissolve the rubber. He adds a thickener, a preservative, and an oil called soya palm stearine, so the candy won't stick to your teeth. After mixing and steaming at 300 degrees Fahrenheit for 4 hours, the batter pours into trays to cool. Sugar, coloring, and flavoring would deteriorate in the heat, so workers add those later. There's enough of this base to make gum centers for 450,000 small Jawbreakers. After 24 hours, the batter's hard. Workers chop it up and blend it with corn syrup to make it softer and sweeter. They add just under 100 pounds of finished gum that didn't make it into Jawbreakers before because it wasn't the right shape. Now they add natural and artificial flavors, which can include lemon, orange, strawberry, grape, even tutti frutti. Then they add icing sugar. It makes the gum smoother to chew than regular sugar would. Workers dump the batch into an extruder that shapes 2 continuous streams of batter called rope. Another extruder divides each rope into 6 hollow tubes. The cavity inside will become pockets of air inside the gum centers. The next machine slices the tubes into segments that are 3 feet 3 inches long. A mechanical arm pushes the segments into the channel of a forming machine. Steel rolls then slice through the tubes and shape them into balls. The balls range in diameter depending on the size of the Jawbreakers being produced. Air blows through perforations in a cooling tunnel to cool and firm the centers. Then they fall into another forming machine which restores their round shape. Other Jawbreakers have hard candy in the center. The machine that makes them works like the presses drug companies use to make pills. It feeds candy powder into dies, then applies up to 5 tons of force to compress the powder into a solid candy. Now for the rest of the Jawbreaker. First, they dump the candy centers into what's called a coating pan. They add a hot mixture of water, corn syrup, and food coloring. Then dextrose, a type of powdered sugar. The pan rotates for 20 minutes as warm air dries the ingredients over the centers. The factory repeats this step 10 times for each layer. Talk about a sweet ordeal. Making a Jawbreaker takes 4 days. Workers give this batch special treatment. They speckle these Jawbreakers with different colors, giving them what this company calls the psychedelic look. After letting the candies dry for 24 hours, a worker adds pinches of powdered carnauba wax. This gives the Jawbreakers a shiny finish. Sliced open, you can see these Jawbreakers have 10 layers of flavors and sugar surrounding either hard candy or bubblegum cores. They measure 2 1/4 inches in diameter, as big as a billiard ball. And if you're counting calories, forget it. A Jawbreaker is 90% sugar. Caviar is made by processing the unfertilized eggs of certain species of fish. For those who love the taste, but not the price, there's simulated caviar made of kelp, a type of seaweed. A fraction of the cost, it looks, smells, and tastes similar to the real thing. Unlike fish caviar, the source of kelp caviar is a plant, so it's fat-free, cholesterol-free, and has 0 calories. This company makes its kelp caviar plain, which is vegetarian, as well as in several flavors. Kelp is chock full of vitamins and minerals, and is especially rich in iodine. Being a marine plant, it's quite different from land plants in that its consistency is gelatinous, which makes it ideal for producing little rubbery balls that resemble fish eggs. At the Kelp Caviar factory, they begin production with kelp that's been dried naturally, then ground into a fine powder. The other ingredients are salt, citric acid, and if they're making a flavored variety, natural flavoring in liquid form. They add the ingredients one at a time to water. The mixer blends them thoroughly for about an hour, producing a thick, gelatinous liquid. They transfer the mixture into a pot connected to an extrusion machine. The machine pumps the mixture through what looks like a shower head. Only instead of outputting a steady stream, it squeezes out droplets, producing tiny kelp balls called pearls, which look exactly like fish eggs. The pearls drop into a coagulation solution. Besides providing a soft landing, this solution helps hold the pearl's shape. The pearls roll down a chute into waiting containers. The water drains out the bottom. Workers empty the containers into large colanders. Then they rinse and strain the pearls to ensure they're all a certain minimum size. Pearls that are too small simply fall through the colander's holes. They weigh out a specific quantity and mix in an all-natural stabilizer required to maintain the pearl's texture and round shape. The factory's quality control lab tests a sample from the batch to make sure the pH level is just right. Careful pH control, coupled with pasteurization, is why this product doesn't require any preservatives. At the packaging station, workers fill glass jars, then twist a tin lid onto each one. Then the jars go into a pasteurization machine. It heats the caviar to a high temperature for a specific period of time, which kills off any bacteria. This ensures a 2-year shelf life without refrigeration. Once opened, the product stays fresh in the fridge for 3 months. After printing each lid with a lot number for tracking purposes, all that's left to do is dress the jar in a cardboard label. Kelp Caviar contains no artificial colors or flavors. Unlike certain types of caviar, it doesn't bleed color to the surrounding food, even when baked. And while real caviar is typically either black sturgeon roe or red salmon roe, Kelp Caviar comes in additional flavors, such as truffle, cognac, and wasabi. The earliest written record of a kite tells the story of a Chinese general in 206 BC who flew a kite over a wicked emperor's palace. He marked the line to measure the distance, then reeled it in. His small army then dug a tunnel into the palace courtyard, launching a surprise attack that conquered the emperor. Today's two-line kite, as the name implies, has two lines to pilot it. It can fly nearly 130 feet high. This kite is made mainly of a lightweight nylon fabric that is waterproof and fade-resistant. It's less than a few hundredths of an inch thick, so it's reinforced with nylon mesh to reduce ripping. The kite's other components include nylon and elastic cords and straps, fittings made of leather, rubber, aluminum, and plastic, and carbon rods. The kite maker starts with a pattern made out of pressed wood. She marks out a piece of the fabric and with a few bricks to hold the fabric in place cuts diagonally. In sewing terms, that's called cutting on the bias. This will stretch the fabric and help it fly. Next, she cuts more pieces of fabric, this time in a different color. This kite has 8 fabric parts that fit together like a puzzle to create an 8-foot wingspan. The kite's left and right sides are mirror images, so there are only 4 different shapes to cut. They range in length from 9 inches to 4 feet. From start to finish, it takes one worker about 2 hours to make this model, called the Dragonfly. First, the kite maker sews the longest part, called the belly, to the other parts. She double stitches with heavy-duty nylon thread to help the kite withstand winds up to 23 miles per hour. She makes tiny incisions along the belly's curved edge so she can fold it and sew in what's called the tension line. Tension line is a type of nylon cord she'll sew into all the seams of the kite's lower sections. It'll give the kite some structure and help keep it rigid while airborne. The kite maker secures each line with a knot, which can later be loosened or tightened to adjust the kite's overall tension. The kite maker uses straps made of very durable yet flexible plastic to line the middle and the edges of the wings. The straps strengthen the kite, enabling it to survive crashes into trees and rocks. After all, what goes up must come down. Next, the kite maker sews a piece of leather called a fitting onto the plastic strap. It's made of leather to protect the kite's structural joints, such as the nose of the kite. It gets a leather patch as well. The kite maker uses a serrated saw to cut the 10 carbon rods to size. They're a 1/4 inch in diameter and range in length from 7 to 32 inches. They form the kite's skeleton, and like bones, they're the most likely part of the kite to break in an accident. But if they do break, it's easy to replace them. A variety of molded plastic, rubber, and aluminum fittings serve a dual purpose. They join the rods together and keep them from falling out of their sleeves. Now, the kite maker attaches a nylon cord called a bridle to the fitting that joins the rods on the wing's leading edge. The bridle is the kite's rudder, steering the kite to the left or right. The bridle comes off easily if you need to replace the rods. The kite maker now attaches tension lines to 2 plastic components called arrows. They're located at the kite's wingtips. She ties elastic bungee cords through the arrows to hold the tension lines in place. This makes all the fabric parts taut enough to fly. Next, she attaches the bridle to the center rod, the spine of the kite.
Their size, shape, and function run the gamut, ranging from beakers and test tubes to petri dishes and vials. Mixing, measuring, storing, or sampling is all in a day's work for a piece of laboratory glassware, built to withstand even the most potent of chemical concoctions. Many scientific breakthroughs are born inside laboratory glassware, the containers scientists use to hold samples for chemical experiments. The glassware starts off as thin glass tubing, stacked by size, weight, length, and diameter. Workers select the correct size for the culture tubes they're about to make and place them in a magazine. As it spins, it drops a tube into each slot on a cutting bed. Then comes the flame. When the heated tubing contacts the wet steel blade, the thermal shock results in a clean separation of the glass. The tubes get a second thermal shock treatment which cuts them to length. Then it's on to the glazing bed. A glazing burner shoots out 1200-degree flames. The heat melts each tube at one end, forming a lip called a glass bead. Just 2 seconds of heat splits the tubes in half and forces the glass bottom of each tube to close in on itself. The finishing fire smooths out the closure. Then, a small amount of air is shot into the open end of the tube to form its round bottom. Now the tubes head into an annealing oven side by side. They bake for about 15 minutes at 1200 degrees. This strengthens the glass so it'll better resist cracking. The heat also sterilizes the tubes. Once the tubes cool, workers collect and pack them. Here, they're making pipettes, long tubes that labs use to transfer fluids. A flame heats the glass to form an indentation which determines the flow rate through the pipette. A wider flame then heats the glass, making it soft and malleable. Large rollers tug at the sides, drawing the soft glass to form the pipette's tip. Now, for the other end of the pipette. Thermal shock is used to cut it to length, and again, a glazing burner forms a glass bead along the rim. A cutting wheel slices through the tip end, creating 2 tubes of identical length. This production line makes vials. These gizmos, called top turrets, feed large glass tubes into a machine. First, a punch-out burner heats the end of the tube to create an opening. Then, a steel pin widens the hole on the upper part of the vial. A forming die squeezes the heated glass to sculpt the shoulder, while a steel plug rises from the bottom to open the vial even wider. Then, a second forming die shapes the neck. Next, a parting burner splits the vial into 2. A bottom turret plucks the newly created half and draws out the soft glass to lengthen it. Fingers inside the turret prevent the glass from breaking. All that's left now is shaping the bottom of the vial. A burner forms a concave base in less than a second. The vials now slide down to what's called an afterformer machine. Here, suction cups lift and place each vial into metal grooves on a printer bed. It's a basic silk screening process, with a squeegee pushing paint through the screen's holes onto the vial. Grippers place the vials on a rack headed for the oven, where they'll bake for about 20 minutes. Finally, a robotic arm whisks the finished vials to packaging. From there, it's off to a blood bank, a hospital, or chemistry class.
Short-sightedness, far-sightedness, and astigmatism are all due to light not focusing precisely onto the retina. Surgeons can correct this by using a laser to reshape the curvature of the front surface of the eye, called the cornea. The surgeon operates on one eye at a time. He cleans the eye, the lid, and the lashes with antiseptic, and administers anesthetic drops to freeze the eye and lid. He opens the lid wide with a speculum, then rinses the eye with a saline solution. Everything's frozen so the patient doesn't feel a thing. Next, antibiotic drops to prevent infection. Before every operation, the surgeon tests the equipment. He fires the laser on a metal plate to test its energy level. The surgeon administers a few more anesthetic drops. Then inspects the microkeratome, the device he'll use to lift a very thin layer from the outer surface of the eye. He also measures the patient's cornea using an ultrasonic instrument. The cornea must be a minimum thickness for it to be safely reshaped. The surgeon uses the speculum again to prop the lid open. Then he begins the operation. He marks the eye with sterile ink, reference marks he'll use later. Next, he positions a metal ring around the cornea. The ring is attached to a suction pump, so it clings to the eye. Like holding a tomato steady while you slice it, it holds the eye steady while the surgeon cuts the tissue. The surgeon lubricates the eye with sterile water, then mops up the excess water with a small absorbent sponge. Then he takes the microkeratome and slips it into the grooves in the metal suction ring. In a matter of seconds, the device moves across the eye, cutting open a flap of tissue, the same way a carpenter's plane shaves a layer of wood. The surgeon uses a sterile sponge ring to keep tears from contaminating the cornea. He folds back the flap of tissue, exposing the cornea. He mops up the excess liquid. Then starts up the laser. Meanwhile, a tiny sponge keeps the flap moist. The laser, an invisible light, fires in pulses 50 pulses per second. Each pulse vaporizes an area of corneal tissue 100 thousandths of an inch thick. The laser has been computer programmed beforehand, so it knows exactly how to reshape the cornea to give most patients 20/20 vision. In less than a minute, it's done. The surgeon removes the sponge, and then, using those little ink marks he made earlier as reference points, folds the flap back to its original position. If the flap isn't precisely where it was before, the patient will have distorted vision. Using a syringe that flushes the area with sterile water, the surgeon carefully smooths the flap, the same way you'd smooth out a tablecloth. Then he removes the sponge ring. Within 45 seconds, the negative pressure inside the cornea sucks the flap back on. The flap literally seals itself. With the sponge, the surgeon dabs up any excess water. He applies antibiotic drops as a preventive measure. Then inspects the microkeratome again before moving on to the other eye. He takes the speculum off, tapes the eye closed, then performs the same operation on the other eye. When that's done, the surgeon uses a high-powered microscope to make sure the flaps are wrinkle-free. The patient wears protection shields until the next morning, then overnight for a week. Briefcases come in many styles today. The classic type is a rigid rectangular box made up of two hinged sections that close together. It's often referred to as an attaché case because it was traditionally the type of briefcase used in diplomatic circles by cultural or military attachés. These luxury attachés are entirely handcrafted, made from English bridle leather, a fine leather traditionally used for horse saddles. The cutter lays out patterns for the various parts, then trims around them. Leather, being an animal hide, naturally has scars and blemishes here and there, so he's careful to select blemish-free areas for use as the main surfaces. Next, he uses a punch press to cut out what are called foundation boards, which will reinforce the leather. At this point, an expert leather craftsman takes over. He positions each foundation board on the leather. Using a tool called a bone folder, he marks where the leather will fold over each board. Then he coats the boards with leather bonding glue and positions them along the fold lines he marked. With a tool called a sleeker, he pushes out air pockets and excess glue. This ensures a thorough, wrinkle-free bond. Next, with a tool called a stitch marker, he perforates the edges of the leather. This ensures the stitching will be straight and evenly spaced. It also sets the angle of the stitches, essential for both aesthetics and durability. Now he bevels the leather. This leaves what's known as a raw edge, which he then colors and seals with a reddish stain that highlights the tan-colored leather. The attaché case frame is made of steel. The craftsman uses contact adhesive to mate the frame to the foundation board and leather. Now he can sew the leather. He inserts an awl in each stitch hole to clear a path through the leather and boards. Then he passes 2 strong saddle stitching needles in opposite directions, pulling the pure linen threads waxed with tallow. Next, he rivets in place 2 traditional style locks made of hand-polished brass. Then, he constructs the handle by sewing several layers of leather around a piece of steel. The handle has a raised rib on the top and bottom. These risers, as they're called, make the handle comfortable to hold. He uses the bone folder to fit a piece of finishing leather snugly against the risers. He glues finishing leather around the handle ends, feeds each end through a brass ring, then folds over the ends to lock in the rings. Then he wraps the rest of the leather under and hand stitches all around. The rings attach to brass handle plates, which he secures from the inside with washers and bolts. Next, he glues in the lid pocket assembly, an all-leather organizer that contains pen loops and pockets for files and business cards. Finally, he lines the bottom section with sheepskin leather that's been coated with a semi-gloss glaze, so it can be wiped clean with a damp cloth. The outer leather is strong and weather-resistant because it's been tanned with natural plant and tree extracts, then conditioned by hand with fish oils and lanolin. Centuries-old techniques they still use to make luxury leather goods today.